Good afternoon, everyone. My name is Kouta Kumamoto. Today I will introduce an interactive learning environment for program design based on the design recipe. Our learning environment is called Ladder. First, let me give you a short demonstration of how it works. The students begins by entering the problem they want to solve. In this example, the problem is define a function that calculates the area of a shape. Then Ladder asked, what is the input to this function? The student answers, a shape. Next, Ladder asked, what kinds of shapes are there? The student answers, a square and a triangle. At this point, to create constructors, Ladder asks about the information each shape has. The student answers saying the length of a side for a square and the length of the base and the height for the triangle. In this way, all the necessary information is collected. Ladder automatically generates the data definition code in Scala, like this. This is how Ladder works as an interactive learning environment. And importantly, because Ladder uses an LLM, it can handle any problem students choose to work on. This means Ladder does not require model answers from teachers. Next, let me talk about the motivation behind this work. The design recipe breaks program design into clear steps, such as defining input data and making a function template. With an instructor, this recipe helps students move from the problem statement to good code. But in the absence of an instructor, students may face several issues. First, with abstract description of the design recipe, they may not know what to do at each step. Second, if they don't have enough knowledge of the programming language's syntax, they may not be able to write the outcomes at each step in a grammatical way. Third, when there is no feedback on the intermediate outcomes, they cannot tell if they are on the right track. To address these issues, we propose Ladder, a natural language dialogue-based learning system. It uses an LLM so that students can solve problems on their own without relying on an instructor. Ladder addresses the issues in three ways. First, it gives step-by-step guidance by asking questions piece by piece. Second, it accepts natural language input and generates code with proper names for functions and variables. Third, it provides feedback at each step, checking the student answers against the problem statement. I will explain these features in more detail later. This is the interface of Ladder. On the left, we have the code preview area. We have the dialogue area. In this area, students interact with Ladder using natural language. On the right, we have the code preview area. This area shows the code that Ladder generates based on the students' responses. We already demonstrated how Ladder works, so here, let me just highlight the simple learning flow it follows. First, students enter the statement of the problem they wish to solve. Next, the student goes through the steps of the design recipe. At each step, the student interacts with Ladder using natural language. When the step is complete and all necessary information is collected, Ladder generates the code based on students' responses and shows it in the code preview area, like this. As you can see, Ladder automatically generates the type name, shape, and the constructor names, square and triangle. The student repeats this process through to the testing step. So far, we have implemented all the steps except the testing step. We realize this running flow by building a custom GPT using OpenAI's MyGPT service. In particular, to guide students step by step in natural language, we specify the detailed conversation flow in the system prompts like this. Ladder, what is the input to this function? Student XX. Since the student input is unknown at this point, we use placeholders like XX. And in later term, Ladder can reuse XX in its questions, like let's define a data type to represent XX. All of these system prompts were actually written in Japanese. After implementing Ladder, we ran a simple user study to whether students can use Ladder smoothly for program design. The participants were 42 second-year undergraduate students in our institution, and their task was to design a program using Ladder and then fill out a questionnaire. In this user study, we used this problem to define a function that calculates the perimeter of a shape. At this stage, we focused on evaluating the usability of Ladder rather than measuring its running effect. This bar chart shows the 42 participants performed when using Ladder. As you can see, 22 students completed their program design successfully. 10 students experienced broken dialogues that went off the intended flow. 4 due to student-side input issues, and 6 due to system malfunctions. The remaining 10 cases include incomplete dialogue logs or access restrictions during use. Here, I will share 2 observations we made from our analysis. We looked at how students actually interact with Ladder and how robust the LLM-based guidance was. First, many students frustrated by dialogue granularity. Second, in many cases, Ladder was able to handle unexpected responses from the students. Let's start with the first observation. In the current version of Ladder, the dialogue is designed to ask very detailed questions in order to support students' understanding. As a result, in the function template step, Ladder asks questions to confirm the content from the data definition step. And in the data example step, Ladder asks about each argument one by one. These detailed dialogues were not always welcomed by students. We often saw responses where they tried to avoid the tedious back and forth. There were 2 main patterns. First, some students asked Ladder directly to skip the detailed questions. For example, in the data definition step, when Ladder asked what kinds of shapes are there, the student replies, rectangles and triangles, that's all, please move on. Second, some students gave several answers at once, predicting the next questions. For instance, in the data example step, when asked about the length of the first side of a triangle, a student answered all 3 sides together, 3, 4, and 5. And in the questionnaire, 16 students also mentioned these issues. Based on these observations, we are now considering ways to adjust the granularity of dialogue. Next, let's look at the second observation. We found that Radar could respond flexibly to students' input. Here is an example from the data example step. When a student gave all 3 side lengths of a triangle at once, Radar confirmed the intention by asking, so side 1 is 3, side 2 is 4, and side 3 is 5. And then Radar skipped the unnecessary follow-up questions and moved on to the next step. This shows that even though the dialogue is fixed in detail, Radar can still make use of the flexibility of the LLM. Next, let me share some interesting results from the questionnaire. We asked which steps felt easier with Radar compared to running without it, and why they felt that way. The most popular step is the data definition. One key reason is that Radar automatically generates English variable names in code, and students found this very helpful. This is an unexpected benefit, and it may be especially useful for students who are not native speakers of English. Next, let me talk about 3 directions for future work. First, we plan to implement multiple interaction levels. As I mentioned, the current dialogue of Radar sometimes feels tedious. We plan to let students choose the dialogue levels based on their proficiency. For example, using cursor questions, answering in code, or directly editing code. Second, we would like to revisit the implementation. While Radar can handle flexible dialogues with an LLM, in some cases, the interaction completely broke down, and we even saw prompt leakage. To address this, we are considering redesigning parts of the implementation, such as using manual control to fix certain parts of the dialogue. Third, we aim to provide appropriate feedback. In our user study, some feedback worked well, like a real instructor, but in other cases, Radar simply gave the correct answer. We plan to improve this so that more of the feedback supports students in revising their own answers. Finally, let me briefly introduce 2 related systems. First, Sys50 Dark is an AI tutor that helps students with programming tasks by answering their coding questions. Like Radar, it uses an LLM to assist students, but unlike Radar, it focuses on coding rather than program design process. Second, Mio is a block-based learning environment that allows students to practice program design following the design recipe. Compared to Radar, its feedback feature is more limited as it does not use an LLM. Let me summarize our work. We proposed Radar, an interactive learning environment based on the design recipe. We hope Ladder can grow into a useful tool for learning program design and help students become better problem solvers. Thank you for listening.
Do you have questions for Kouta?
Thank you so much for your talk. I was wondering, so oftentimes in a class, we have students with different levels of understanding of the coursework, of expertise. Do you think the level of granularity has some connection with the experience that these students have, or are there any other factors that may contribute to having all these different levels of granularity to help them understand how to program?
Thank you. So, sorry.
I can repeat the question. So do you think so the question is if the level of experience of users may have an impact in the way we, for example, design the different levels of granularity in Ladder.
So let me try asking this in a slightly different way. If I'm a very experienced student, I might get very annoyed if you ask me lots of small questions.
Yeah.
If I'm a very I'm a student who's struggling a lot,
Yes.
and you ask me very big questions, I won't know how to answer them. Does that make sense?
Yes.
So I think one way I would phrase the question is, shouldn't you make the questions based on the student's ability so far? Does that make sense?
That is how measure the student levels?
Well, that's your problem, not ours. That's why we're on this side of the stage and you're on that side.
So.
I'm Kouta, so maybe I would add some answers. So what he's currently thinking is just to offer multiple level of granularity so that the student can choose their own preferences, but it might be also nice to think about to measure the student's abilities and automatically select that. So.
There's a long tradition of adaptive systems that do this, right? The entire adaptive tutor literature and so on. So we have ways of doing it, yeah.
All right. Other questions? Yeah, okay.
Thanks for the talk. It's a question for you on the DAISY talk this morning. You have 42 students, and you have 42 students.
Yes.
Why? Is it like a standard number in Japan? You have 42 students per classes. Oh! Thank you for the answer.
Yeah. Thank you for the talk. So how do students know how to answer the question, what is the input to this function? In the book, Animated Problem Solving, this question is answered by teaching students how to perform an extraction step over similar expressions. So how do you guys approach answering this question?
Sorry, could you repeat the question? Sorry?
So how do students know how to answer the question, what is the input to this function? In the book, Animated Problem Solving, this question is answered by teaching students how to perform an extraction step over similar expressions. So how do you guys approach Or how do your students answer the question? What is the input to this function?
Your question is, what is the correct answer?
How do your students answer the question?
Okay. The many of them answered shape.
So I believe in one of your steps of the design recipe, you asked, you guys are asking the students, what is the input to this function? Yes. So how do your students know how to answer that question?
Sorry, the question is?
How do what is the input to this function?
What is the input to this function?
Yes, so like.
The original question. So the question is, how do students know how to answer the question, what is the input of the function?
Okay. The students knows from the problem statement. So,
I guess, so I'm teaching that course. So in that course, every time we develop a function, we go through all the steps of the design recipe. So the students should be able to answer this question if they understand the design recipe correctly.
Yeah, so it's a question of the scaffolding, right? Does it answer the question? Do you have a follow-up question? So it's.
I'm just more curious about, I guess, the difference in teaching and pedagogy, because within how we teach the course in the design recipe, students are taught to perform an extraction step over the similar expressions to figure out the inputs to their function. So how do you guys teach students to figure out the inputs to their functions?
Is this extraction part of the recipe?
It's usually implicit, and since this is a very introductory course, the functions students develop are usually very simple, so it's easy to find the input. But on the other hand, in this experiment, we had several students answering something like the size of something like that, instead of saying shape.
Thank you.
Okay, yeah, let's thank the speaker again, Kouta.